Recording in progress. Hey, everybody. I'm not Lisa. And those of you who were here last time are going to hear the same thing. Hi, I'm not Lisa. I happen to know Lisa. I know Lisa, I think, fairly well. Um, yeah, talk. I don't want to go down that path. I'm going to shut that door right now. But that being said, uh, Lisa's currently a jurist in a trial. And so she believes the trial will go quickly and believes that she'll be back Thursday. I don't know if that's the case. The legal system is messy, I hear. So we will find out if that's truly the case. But she'll, of course, let you know. Um, as I mentioned in the last class, I'm reminded of a Key and Peele sketch. Mr. Garvey, I'm your sub. For those of you who remember Key and Peele, look that up. Just insubordinate and churlish. That's me. Anyway, then next, I've been given a set of instructions on what to present today. I'm not familiar with what you know so far, though, so I'm sort of coming on board. I've got. It looks like you have actually three great teaching assistants in this class, right? As Cass is involved in this, or is she with the other one? SCM. So you have two great teaching assistants. Here I am trying to not steer you away from one of them. Well, one of your teaching assistants is great, but I can't tell you which one. No, that's not. Yeah, but let's not go down that path. You have two great teaching assistants, but you'll keep me on track if I am going over things too slow, right? Everybody, help me out here. Okay. Um. So I've been left with some instructions. I have Lisa's materials. Oh, let me give you background. Who am I? Jonathan Templin, professor in measurement statistics, EF Lindquist chair. I've been doing this stuff for a while. I'm trained in quantitative psychology, got a PhD from Illinois in quant psych, master's in statistics, master's in psychology, yada yada yada. I call myself a psychometrician, and you're like, wait, this is generalized. There's no psychometrics here, and yet it's the core of a lot of what we do in modern psychometrics. So without knowing this, you can't do item response theory. Without knowing this, a lot of other methods start to become confusing or otherwise cumbersome. So knowing this helps put a lot of the future work that you might do into perspective, not just in psychometrics, but elsewhere too. Looking at all the posters. Mixed feelings about posters. I think that is an accidental unmute, so I'll do that. Okay, next. The other thing about this is I absolutely encourage your questions. So anybody in class, you're great. But I feel like I give priority to everybody on Zoom here. Hi, Zoom. How's it going? Thank you, Sora. I'm not recording this, so I'm going to say hello. Sergio gives a thumbs up. So that means if I see a hand raised in class, but you're on Zoom and unmute yourself, guess who gets to go first? Zoom, even though people are in class. But I say that to try to motivate you to try to interact with me. I accept things like, where is it here? Like you can do all sorts of stuff to like make me go, what? And I'd love it. So just be on your toes, all right? Help me out here. Like give me some icons, some thumbs up, something like that. And in class, you can just hand gesture with me. And you know what I'm talking about. Be like, yeah, that's terrible. All right. So that's that. Let me actually I am recording. I'll cut the first part off. Let's get started. Shall we? I understand you have been on quite the journey in this class so far. You've had to deal with interaction terms, simple slopes, main effects. How'd that go? Anybody want their money back yet? Probably not. And now we're doing what with logits? If I asked you on the street before this semester what a logit was, who could answer that? I think the answer would be, are you speaking my language? Oh, you could? Log log of odds of probability of one. That's Lisa's drill. I get it. I get it. But could you have answered that a month ago or 2 months ago? Probably not, right? No. No. This class is all about the concept of like if all you knew were what you learned from intermediate or your linear regression class or your linear models class, all you would have are data that are continuous. And we know that that doesn't work out. So what do we do when data quit being continuous? Continuous and hopefully nicely symmetric and conditionally normal. This class is all about that. And it's such a hard step to go from everything's normal because you can write an equation that just shows it to weird old things called logits or probits or tobits or you name it. There's all sorts of its that are coming, right? Odds. So we're going to cover, I'm supposed to cover what you did last time, but do it again. Did I do that? Slides 1 through 16 of this?
That sounds right to me.
Okay. We'll see how this goes. So I'll dive right in. Generalized linear models for binary and categorical outcomes. Today it's just the binary part. Categorical takes what you learn from binary and just ups the difficulty level a little bit more. The bigger picture of generalized linear models is this. You got data over here, a non-normal conditional distribution of y. What is that? Non-normal means not the bell curve, not nice symmetric looking thing, right? Not a normal distribution, sometimes called the Gaussian distribution. The problem with that, let's think of the binary variable, right? The binary variable is a 0 or a 1, right? It's sort of the basics for what you're trying to predict in a logistic regression. If the binary variable is 0 or 1, what does that mean about, what does that say about the range of what the mean can be for a binary variable? Where's the mean? What's its boundary? 0 to 1, right? And therein lies the problem. If you predict the mean and your prediction for it is 1.5 and the boundary of it is 1, that seems like that could cause some problems in your analysis, right? It certainly would draw into question a whole lot of what you're finding for your parameters. So what we have to do with the mean is we actually apply a function to it, this link function. And it basically says, yeah, we'll take the mean, but instead of keeping it between 0 and 1, we're going to make it map onto the entire number line, right? From negative infinity to positive infinity. I know infinity sounds threatening. As I tell my son, infinity is just a concept. It's not a number, right? So we could have like an infinity of 20 if we needed to. Nobody's threatened by 20, right? Anybody? Oh, never mind. Looking at Zoom. Anybody who? Never mind. I was just gonna goof off in Lisa's class. Hey, what'd you do in my class? I just told jokes and nobody cared and nobody liked them. They weren't even funny. Anyway, so what we need to do to model the mean, because we have a bunch of, you've seen linear regression, right? The parameters are continuous. They can be any number. That means when you predict a number, it can be any number from negative infinity to positive infinity or 20, right? It could be any of that. We need a way to map the number from linear regression onto the 0 to 1 space. Or backwards, we need a way to take the 0 to 1 space and map it onto all the numbers that are possible. That's what the link function does. So we take a link function, we apply it to the mean of the data, and we end up then predicting that link transform mean, right? That's the weird part, right? So it's like data, parameters get passed through a little bit of a function to build this. Now, I will note, I said something incorrect when I said apply a link function. We're not applying a link function to the data itself, right? Because as JC mentioned, logit is the log of the blah, 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 right? But it says log. How many of you are super familiar with log functions? Don't have to be super familiar, but let's try it this way. A log of 1, doesn't matter if it's natural log or log base 10 or whatever. A log of 1 is 0. What's log of 0? Undefined. As the number becomes decimal and it goes from 1 closer to 0, the log approaches negative infinity. But it's not defined. So you can't apply a log to your data. We're not taking the data and transforming them. In fact, this whole class is about don't transform your data. For so many years, we transformed our data to fit what we think about normal. What we're transforming, though, is the mean of the data, right? And it's not even direct in that. We're not even like, We actually do it all through one single process. We're not applying a transformation ourselves. The software does that in the estimation process. So that's the main thing. How are we doing? Did you hear that the last time? Do I need to cover that again, or is it good to cover this again?
It's good to cover it again.
Okay. Okay. So, the problem with non-normal data is that we have non-normal means, and the problem with non-normal means is we can't use a normal distribution for it. And this whole time you were doing linear regression, didn't you know the part that wasn't the error was telling you what the conditional mean happened to be, right? So it was predicting the mean. And we did, depending on the class you're in, sometimes we emphasize that a little bit, sometimes we emphasize that a lot. But in generalized models, it's almost always the case we predict the mean. And then when you get further along, you might predict the variance too, but that's not in this class, right? So it's really this is the step into taking what you already know about linear models, because the interactions, we keep them. The simple slopes, the main effects, the building of a model, the design, the connection between study design and model parameterization, all of that will still hold. It's just you'll just put it in a different function in R, or a different package in R, or a different whatever formula in SPSS, whatever you use. Lisa, by the way, the other day was telling me how much better SPSS is now. Anyway, all right. So non-normal distribution of Y. Then link function, other distribution. Oh, hang on. General linear models use the normal conditional distribution. I'll just give the highlights here. The normal distribution we know has a mean and the variance. The mean part from a linear model comes from the predictors and betas, and the variance comes from the residual variance, right? Other distributions are more plausible when we have non-normal data, and in particular, this case where we have binary data. That is a particular big problem for normal distributions, because effectively in binary data, the mean and the variance are functions of each other. Meaning, if we know the mean, we know the variance, but the normal distribution, they're separate. So when we know the mean, we still don't know the variance. We have to estimate them separately. So if we just apply a normal model here, we've got a couple of problems. One is we have two parameters to the job of one. Another is our prediction may go out of bounds. So that's bad. So not all distributions, though, have those, like you've seen before, a mean and the variance. So we go from there. All right. Why do we care about this? The main part of this is all of our model can be wrong if we don't model the right distribution for the data. That's it. All of our inferences we make from our model may not be accurate. That goes from the point estimates of the parameters, right? Your betas, to the p-values, the standard errors, all of it can be off. So, all right. So link function, G. I don't know why they picked G, but whatever. G with a dot in the middle. That's our way of mapping all the fixed effects, the predictors, onto the range of the mean itself, right? And similarly, what can be done one way can go the other way in reverse. We could go back. Once we have our model parameters, we could go and put them in the link function, the inverse link function, and convert them from a number that's all the way continuous, real number line stuff, to a probability, right? We can transform from probability to logit and logit back, probability. And this allows us to predict values that will be within bounds, meaning we will predict the means of people, and those predictions will be between 0 and 1 for binary data, bless you, or they may be whatever the range of their mean happens to be for the other distributions you see as well too. All right. Again, we are talking about the conditional mean. So meaning the mean conditional on all the set of predictors and fixed effects, or betas, in your model. And so if you have a binary outcome, you will predict a probability of that outcome, the mean of it. When you have a count outcome, your conditional mean is an expected count. It's above 0, or it's 0 to infinity. It doesn't go negative. You can't have a count that's negative, at least not in observed data. And then, so the mean will also be between 0 and infinity, but will not be the actual count itself. It'll be um, some number, some decimal number in between there. All right. And so, really, to reconcile everything, the normal distribution, what we had before in linear regression, you were predicting the mean, but you weren't doing any transformation of it. And that's why, if we talk about it being something called the identity link function, in math, we often use the number one to refer to the identity because anything times the number one is just itself, right? And so the identity link function is what's called, which is kind of funny. It's kind of like um, updating history, because in the history of statistics, like linear regression came way before logistic regression. And I don't think we fully understood what we were doing. I mean, some people certainly did. There's some brilliant people to it. And then they got to generalize and like, oh yeah, well, we were doing that already, but it was just multiplying it by one. And it's like, come on, man, really? Anything you got to be like, my argument is I multiplied it by one. Not a good argument, but it does fit into that framework, right? Questions? No. This is Lisa's link function. What does she mean? She won $10, but there's a multiplier. Multiplied by one. Nice. Nice. I don't condone gambling. So Lisa and I disagree about gambling quite a bit. I'm just kidding. When she comes back, if she shows you this slide, you should just give her the number to 1-800-BETS-OFF. In a previous life, I may have collected data from a gambling casino before and had fun with that. And got to gamble with grant money. So if you ever want to know the result of that story, how I gambled with grant money, literally, legitimately gambled with grant money, you have to take one of my other classes. There we go. Try and drive traffic to my class. Don't gamble, all right? Anyway, where is that? Is that South Carolina? Yeah, it is. That's a. I now I know where this picture came from. Anyway, got it. Okay. Finally, we got non-normal data, meaning our mean doesn't go between. It's bounded, I guess. We've got a link function to unbound the mean, but what do we do to predict it? We predict it with something called a linear predictor of fixed and sometimes random effects. In this class, I think you're all fixed. I don't know, later on she adds random, I don't know. But generally speaking, the fixed effects are the betas that you see in your model. The, the core distinction, if you're wondering what becomes fixed versus random, is if you say that parameter has a distribution attached to it for whatever reason, it's technically a random effect. And if you don't, it's called a fixed effect. That's a trivial piece of information. Use that in your next stats trivial pursuit party. I know that's really popular. I can give you all sorts of fun stat trivia. No, never mind. I'm trying, guys. I'm trying to get everybody engaged. I'm trying to make you like me better than you like Lisa. And that's a tough challenge because she's really good. I know. I know firsthand. But I'm still trying because I'm a competitive person. Yeah, it's a. Oh, no. And see, that's the thing. She'll sing and I won't. There will be no singing today. There needs to be something other than water in here if I'm going to sing. Let's just put it that way. And not Coke. All right. Linear predictor is what you've known already. It's your set of fixed and random effects. Everything that goes in there, you already know about. It's still the same, right? Main effects, interactions, conditional parameters, so forth. Um, we can still use a lot of the language on those parameters directly for what we do. But when we use the linked function, we sort of lose a little bit of proximity to what's going on in the real world. So sometimes we have to go and translate things back, going back to probability or going back to odds or whatever you need to do. And that's where the inverse link function comes in, right? Not a lot of people in the world who don't train in this way, except for you, um, think in logits. It's very hard to think about. You're sort of removed from your data. Whereas thinking of, oh, the increase in this is, the probability of this happening under this condition is 0.5 and the probability of it happening under that condition is 0.9, you can probably evaluate that a little bit easier than thinking of the logits for it. So, all right. Questions? All right, let's talk about what would happen if we tried to fit a normal linear model, general linear model to the binary outcomes. Right? So if we have one y variable, y that's an outcome, it's either 0 or 1. Um, Given each person's set of predictors, what we're trying to predict is the conditional mean, the probability of having a 1. Now, one thing I will note, it's a little bit weird, but it sort of describes if you I think if you talk about it now, I think it sort of allows for a little bit more mental flexibility going forward. In a binary outcome, part of the weirdness is I know what your value is or what your there's two values your data can be. Right? So if I'm trying to model the probability of a 1, there's something called the what is it? The oh my god, I'm blanking on the term. Starts with a C, the converse? No, complement. Complementary probability, right? The probability of 1 has to sum with the probability of 0. Sorry for your ears with that clap. That was louder than I expected. But I nailed that loudly though. The complementary probability. So what does that mean? Some people like modeling the probability of a 1. And then there are other people who like modeling the probability of a 0. So you may see this in different forms, and we're going to talk about that in a couple slides, why some things sometimes are called intercepts and sometimes they're called thresholds and so forth, right? But they're sort of, it's very related. It's some slight changes here or there. Um, so remember, the conditional mean has more possible values than the outcome, right? The conditional mean is somewhere between 0 and 1. The outcome is either 0 or 1. So under a general linear model, we could try to put the mean of the variable out here, although that doesn't really make a lot of sense because everybody's got the same mean, but just hear me out here. If we predicted the mean, right, we can put in a prediction function of two variables, x1 and x2, with some error. And here, we can interpret them the same way, like, beta 0 is the probability of, the probability of y equals 1 when all the predictors are 0 and so forth, and you can talk about expected change. But what could possibly go wrong with this is, yeah, those pink lines are the 0 to 1, and we could quickly run out of bounds with that prediction. And can I give you a sidebar? Are you familiar that Lisa does not like R? You familiar with that? Does she make that a point? Okay, just want to make a point about this. So I'm given a workshop. I converted all my stuff to R when I moved back to Kansas about 2014. I've been using R since literally like 1999, 1998, like early R, right? Hated it, realized I needed to change, yada yada yada. So I'm given a workshop in 2016 in Hilton Head, South Carolina, and like Lisa and I put on this stats training called Stats on the Beach for a couple of years, and then we realized we just like the beach and not the teaching part. Um, and so it was awesome. So I'm given an example on the fly using a model in R, a diagnostic model, which some of you know about. You don't have to. Anyway, long story short, it comes up with predicted probabilities, and the probability it gave me for a data set in the book I wrote that they hijacked and put in there, 1.2 in front of everybody on the video, probability of 1.2. So what is that like when you see that in an R package? Guess what Lisa would have to say about that for her R package? She's like, I'm going to use that example forever. You get what you pay for, which is what I tell her something whenever SAS or M Plus doesn't work. Hey, at least R didn't work and it was free. But the point I'm trying to make, but the other point I'm trying to make is this is bad because if someone's like, yeah, my probability of that happening is 1.2, even if you're not familiar with logits or whatever, that can't happen, right? What does a probability of 1.2 mean? It doesn't even make sense. Or a probability of negative 0.2. What's that? Like, oh, the probability was so low it started coming back up again or something like that. I don't know. So bad. Not only is it bad from a math standpoint of view, because you can imagine whatever made the prediction this big needs to stop being that big, right? So the parameters have to adjust. Um, Second, it sort of gives the indication that you probably don't know what you're doing, right, with your data, which is what I got when I saw the probability of 1.2 in R right on my screen. So we need something to shut down those lines. We need to make this, would she say bendy? Oh, I got that one. I'm trying. I'm not Lisa, clearly not Lisa, but I'm trying. We need to make it bendy. And that's where things get a little bit weird. How are you on odds?
You should definitely re-go over them.
Let me put it this way. First, let's talk about probability. If I got a coin and I flip it and it's a fair coin, what's the odds? What's the probability it lands on heads? The probability. Like a coin has head side, a tail side, right? Flip the coin, do that process an infinite number of times. And again, infinity, I think I said this in the last class. No, I said it to you, right? Infinity is a concept. So infinity could be 20, right? Right? What is the long run probability that I'm going to land heads on that coin? 50%, right? So a proportion would be 0.5, right? And so, from a conceptual point of view, before we do any of the math of it, what's the probability I land on tails then? It's the complement, right? 1 minus 0.5. So it's 0.5 for heads, 0.5 for tails, right? So in that one case, the probabilities are equal, right? One way of expressing that equal probability is to change from probability to odds. Odds is a way of describing uncertainty that tries to do so in more of a numeric sense, a little bit more of a like whole number sense, right? Not always whole numbers and odds, but just from a conceptual point of view. So, in that same setting, where technically we define the odds as the probability over 1 minus the probability, but we know 1 minus the probability is the chance the other thing happens, right? The chance of a heads is the numerator, the chance of the other thing is the denominator. So what odds is doing is telling us what is the relative likelihood that the thing in the numerator happens compared to the denominator, right? And trying to put that into better words, although they're confusing at first. And the way that we look at that, if I put 0.5 in the numerator and I put 0.5 in the denominator, the odds of finding a heads is 1, right? And that's the core to me of like when you're thinking odds, find the 1. 1 means equally likely, right? Now, if I came in with a loaded coin and I flipped it 100 times and 75 of them were heads, meaning 25 were tails, right? So now think about this ratio, right? It'd be 75 over 100 for the numerator and 25 over 100 for the denominator. Turns out, if you remember the heuristic algorithm to get rid of to do division, right? It was 75 over 100 all over 25 over 100. Do you remember the algorithm to deal with that? The invert and multiply. I don't remember the number sense for it, but basically those hundreds go away, leaving us with 75 over 25, which equals 3. And so in that sense, what that's telling me is heads is 3 times more likely to occur than tails, right? That is what odds is telling you. What's more likely to occur? Now, I'm pretty sure, again, oh boy, let's see if I get in trouble for this. I'm using a university computer and I'm going to betmgm.com. So, let's talk about odds and uncertainty a bit. Hey, Lisa dropped the scratch off ticket in. I'm just going to go to the casino and the sports book here, right? So, believe it or not, you can read this as odds too. They're a little bit more difficult. But here, this is sort of what will happen if you put in this is the amount of money. If you see a negative here, it's the amount of money needed to win $100, right? So what's saying is in this game, this first team, the Boston Celtics. By the way, I don't even know what game this is. It's like basketball. I don't need you to know sports, but think of it from an event. This is a sporting event where one team is going to win, one team's going to lose, and we can think of what we're trying to predict is the probability let's say the top team, the Celtics here, wins, right? Well, I don't know. I don't follow the NBA anymore because I'm a Sacramento Kings fan, which means I just live in misery all my life, right? It happens. It's okay. It's a childhood team. It's an obsession with my youth. I'm working on it with a therapist. It's okay. But the bigger picture is I have I can tell you that this team has 41 wins, this other team has 21. So I would assume that the team with the 41 wins is more likely to win. So when you look at this money line here, basically this is telling you if you put a bet of $375 on the Celtics and the Celtics win, you get $100 back. And if you put a bet of $290, or sorry, if you put $100 on the Nets, you win $290. Right? And so that's what that's trying to give you is the odds that one of them will win. And actually, there's a formula you could actually go and compute from here to tell you what the odds of each one being are. And then you can backwards translate that back to probability because any odds can go in reverse to probability and figure out what the casino thinks the probability the Celtics will win the game will happen to be. So when I talk about odds, we can talk about gambling. Another place where you see a lot of odds is in healthcare, in medicine, in a lot of statistics journals in medicine, talking about the odds ratio or the odds of something happening. And that's basically what is the, and it's another way of expressing uncertainty in prediction, but it's not really great. I don't think in odds. I think Lisa said the same thing. She doesn't think in odds, right? I'm not sure. So I'm like, Elisa, the odds it's going to happen is 4-1.
Zero is still zero.
4 times 0 is still 0. By the way, this is one where you'd say it's 3-1. There are 3 parts up here to 1 at the bottom. Sometimes you hear odds expressed that way. The ratio of odds is 3, right? So it's 3 times more likely. So if you think of odds as 3 times more likely, it's great. Here's the problem with odds. 2 problems. If you take a decimal number between 0 and 1 and divide it by a number between 0 and 1, the range of that outcome goes from 0 to positive infinity. That gets you half of the way to where you need to be. We need that negative side for us to use in a linear model. We need the whole number line, all of the negatives. There's another problem with odds. I don't think it's a problem, but it just confuses my mind, right? I made this odds ratio. I said the odds, I flipped my loaded coin. I flipped it 100 times and I saw 75 heads. The odds of a heads is 3 times more likely than the odds of a tails. But I could have done it differently. Whoops. I could have said, what's the odds of a tails? Right? And in here, it'd be 25 over 100 over 75 over 100. Those cancel, leaving us 25 over 75 or 1/3. Right? That sounds weird. The odds of a tails is 0.3, 0.333, right? Which is approximately 0.333333, right? That's weird. What's the odds of tails happens? 0.3. Now, the way that you would interpret that is a tails is a third less likely, or it has a third of the likelihood of a heads, right? Or for every 3 heads, there should be 1 tails. That's how to sort of interpret it. But that's hard when odds are between 0 and 1. The thing I'm trying to make odds for, the numerator, the tails in this case, is less likely to occur than the thing in the denominator, the complement for it, right? How am I doing with odds? So? Okay? All right. All right. So then moving back. So, now this is where logit comes in. The logit itself, if we took a log of the odds, now we get everything that we want when it comes to modeling. Remember the log we mentioned in class, the log of 1 is 0. The log of, so think of it this way. That first example with the fair coin, the odds of a heads was a 1. The probability of a heads is 0.5. The log odds, or logit, of heads was the log of 1. And the log of 1 is 0. Right? So we have a 50% probability, or 0.5 probability, or 50% probability of um, of a heads. We have an odds of 1, meaning equally likely to see heads or tails. We have a logit of 0. So when you're thinking of this weird scale for each, try that translation. I always start with what 50-50 is. 50-50 probability, 0.5 probability, odds of 1, logit of 0. All right? So then the neat feature about the log function is any number between 1 and 0 is negative, right? The log of a number between 0 and 1 is negative. In fact, it gets increasingly negative as that fraction gets closer and closer to 0, right? And it goes to negative infinity. Likewise, anything above 1 is positive. And that function itself, as the number above 1 gets more and more positive, the odds is more and more heavy, it will trend toward positive infinity above 1, right? Which is a little weird if you think about it, right? What we're doing in odds, I said, oh, look at this. The odds of 1 equals probability 0.5, right? The 50-50 spot where everything's equally likely. Anything above 1 means the numerator, or the target of the probability, is more likely to happen. And there's a lot of numbers above 1, right? It goes to literally positive infinity. Again, a concept, but still, that could be really big. It could be 100,000. Oh, it's 100,000 more times likely to happen, right? Okay. And then between 0 and 1 on odds is the other half of that infinity, right? Which seems weird. We have between positive 1 and positive infinity of the number line to describe when the numerator is more likely to happen. But we have only between 0 and 1 to describe when the denominator is going to happen. And that's the weird thing about numbers, is that between 0 and 1, there's an infinite number of fractional values, right? Just like above 1, there's an infinite number of values. So it's, to me, the imbalance in that is weird. You have to sort of do a little mental gymnastics, but it does fit with the logic of mathematics. It's just weird math. Logit, on the other hand, right here, keeps it symmetric, right? When the target is less likely to happen, that's negative. When it's equally likely to happen, that's 0. And when the target is more likely to happen, it's positive, right? So logit, I think, fits a lot more symmetrically with probability, because probability at 0.5, it's equally likely. That's logit of 0. At less than 0.5, not the target, the complement is more likely. That's negative logit. Anything bigger than 0.5 is more likely, and that's positive, right? So that symmetry seems to fit. And there's, I made that figure. I kid you not. That was from a job talk I gave at Nebraska in like 2011. Anyway, I take a lot of Lisa's slides, so fine. I made that one. But that's the thing about logit. The other thing I want to note is, let's talk a little bit about complementary probabilities, right? Remember what a complementary probability is? Like, if the probability of a heads is 0.75, the probability of not heads, or tails in that case, is its complement, is 0.25. And we know with probability, when there's two outcomes, that the probabilities have to sum to 1, right? So that gives us a kind of a symmetry, right? 0.75, 0.25, 0.9, 0.1, those things. Turns out that symmetry is repeated on the logit, right? So remember, logit of 0 is probability of 0.5. That's right here in the middle. A probability of 0.9 has a logit of 2.2, right? What's the complementary probability of 0.9? 0.1. So the complementary logit turns out to be negative 2.2. It literally is putting a negative sign in front of it. It's still expressing the distance between uncertain, which is 0.9, and certain, which is 1. In the lower case, it's 0.1 to 0, right? It's how far the uncertainty goes. The closer the probability gets to 1, the more certainty we have, or vice versa. The closer it gets to 0, the more certainty we have, and the logit scales accordingly. So then the logit model scale of 4.6 for a probability of 0.99. What's the logit of a probability of 0.01? Negative 4.6. Right? Complementary. The other thing to note on this, the scale of logits is weird, right? When you think of linear regression, the scale of the parameters depends on the outcome variable scale. And in some cases, the predictor variable, right? A beta is units of y per units of x, right? In logistic regression, we're actually in logits. Logits of y per units of x is what we're after. And so what that means is this scale, this logit scale, is important to memorize. If you get output in the computer and you see like an intercept of 5, that's on logits. That'd be like saying when all the predictors are 0, the probability is really close to 1 that this event happened. It's weird, right? Logits have a scale between, basically their numbers are between -5 and 5. That's where you expect to see most logits. If you don't see a logit in that range for certain parameters, start to think about it. It's a way of looking at your data. And again, the beta parameters are really logits per unit of x. So those can get a little weird, but the intercept itself always between the negatives, -5 and 5. How am I doing? Too slow? We're okay? How's Zoom? How we doing, Zoom? I don't see any face. Yeah, question.
Can I ask a question then?
Yes.
I mean, so is there a specific range for logit too? Because the probability says like if it is 0.99, then the logic should be 4.6. So if the probability is 1, then what is that for
That's great.
logit?
So it turns out a probability of 1 can't happen in a logit. Because take a look at what happens with the probability of 1. Well, the probability is 1, and then the
Yeah,
numerator, the denominator, right? So you
I
can't be
see.
1. But let's take a number just infinitesimally close to 1. Like just take off, subtract 1, scientific notations 1 to the negative, 10 to the negative 100th power. Logits do go up to negative or to positive infinity in that case. So a
Okay.
probability of 0.999 where there's 100 nines afterwards is going to have a logit that's probably 100, 200, you name it. But the key in thinking about it is for if you look at the probability of 0.99, probability of 0.99 describes an outcome or an event that's almost certain to happen, right? 1 out of every 100 times that event will not happen. That's very rare. The logit according to that is 4.6.
Hmm.
But between 0.99 and 1, all the other logits go from 4.6 to positive infinity, right? It just gets really spread out. And so the point in thinking about that is trying to get your brain to think about when I see a logit of 4.6, that's a really big logit. It may not be really big because it doesn't look like infinity, but when I convert that to a probability, that basically indicates this event is almost certain, right? We have a lot of certainty to that. Does that help?
Yeah, sure. Thank you.
Thank you. Yeah. Yes. That's where the bulk of the what we would call it to be. Yes. No, no, I misspoke when I said generally it's between -5 and 5. What I should have said is -5 to 5 covers most of the probability between 0 and 1. Here, let me give another example here. This slide shows it, but let me just pull up my friend. No, that's not what I want. You're not my friend. How about some R? This class is getting real if I'm going to R. Does Lisa use R in this class? She does. She has all the R packages, right? Okay, where did R Studio go? Come on, R Studio. I don't know about you, but my R Studios are taking forever to like initialize these days. I don't know what they've done. But let's do this. Okay, so the probability is, let me just show this. Log prob equals 0.9. I'm just going to make a quick little function here. There. Okay, so now that is a logit of 0.99. It's 4.6, right? I had another one there, 0.999, which is just 9 thousandths more of a number. And now my logit's 6.9. Now, guess what happens if I add one more 9 to it, right? It's just going to keep getting bigger and bigger and bigger. But functionally speaking, I don't know about you, but I cannot tell a difference in statistical terms between a probability of 0.999 and a probability of 0.99999, right? And the reason for that is to be able to distinguish those two numbers, think of how big our sample would have to be to reliably estimate a probability of either of those, right? So functionally speaking, what I should have clarified was that range of -5 to 5 is where it basically runs between 0.995 and 0.005. Let me try that. I'm trying to see. Yeah.
Way to think about this, be also with like the normal distribution and like one standard deviation, you've got like 68% of the data.
That'd be a good way of thinking about it. It's like saying, what is the range of the probability? The range of probability. So basically, I'm trying to get this as close to 5 as I can to see what that range is, right? And I'm slowing down here. Oh, I overshot it, right? You can see how hard this is. Nope. 3.335. Okay, that's close. All right. So between 0.99, can we just say 0.9933? Is this close enough to 5 for everybody? Okay.
I'm kidding, I'm kidding, I'm kidding.
You know, Lisa, I was going to get through class, and Nikki had to argue about tenths of thousandths of fractions of a percent. But it sounds like you don't want a TA anymore. Let's see here. This is 0067, I think. There's the negative value, right? So what I'm saying is, when I say -5 to 5, that's literally ranging between, what's that, 6 thousandths of a percent, all right, and 99. So the bulk of what we're talking about, like that middle range, is covered by -5 to 5. And then even then, if you want to map on where the middle 68% is, that's going to be weirder also. But the key in understanding, to me, logits is remembering that mapping, because logits are the scale now of the outcome. We used to say, oh, as x goes up 2, y goes up 50 or something like that, right? Well, now we're not going to say, in x and y terms, y went up 50. 50 of what? Well, 50, whatever you're measuring, 50 points of happiness, $50 of income, whatever, something along those lines. Now we're not talking about that. We're not talking about data directly. We're talking about logits. So y is no longer on its original scale. It's on the logit scale. That's the key to me. All right, other questions? This stuff is hard. I think Lisa says that, right? I'm trying to hit all of her catchphrases without singing. It's not happy. Why would, it's just garbage. I guess it's happy if it stinks up my garage. Whew! Get that garbage out. Sorry. Here's what I would ask you to do. If she says happy garbage day, will you please ask her, is it happy? And just don't tell her I said that, and let's see if she listens to it. Okay. I know. I don't know that she's going to listen to it. Lisa, if you're listening to this, you got to find something better to do with your time. But that being said, I don't know if that's going to be on YouTube or not. Okay. I'm trying to have fun with this. I hope I'm enjoying myself. I don't know if you are. So if I ask you what a logit is, JC answered the question begin, but let's talk about it again. What's a logit to you? That's an open-ended question. I would go with a couple things. How about I give it to you what it means to me? It's a way of modeling binary data. That's the main thing. It has a scale unique to itself. It maps probability onto a number line where the bulk of those probabilities somewhere show up between -5 and 5. And honestly, when you really get into logits, I find them much easier to work with than odds, mainly because that symmetry of the negative, the positive, and where 0 is mapping onto the probability range of 0, 0.5, and 1. How's that? That help? A little bit better? Okay. Now, this is some of the other things. This is the mapping. This is the probability. This is what I was, this picture that you see on the screen here is what I was doing with R. Basically, I was trying to show you what happens. Like this probability of 0.05 turns into be a logit of -3, right? Positive 0.95 is a logit of 3. It's sort of mapping the probability metric. This graph I don't particularly care for, mainly because if you think about it, it's arbitrary the distance between the points at the top and the bottom. So I could have drawn it in many different ways and it would have looked a little bit different. I kind of prefer this picture right here personally. But then again, I made that. Rod McDonald said of some of the colleagues in the field that I don't believe he cared about much. He said, well, the way I think about him is he only steals from the very best. Just kidding. I shouldn't say that. You should see how many of Lisa's slides I have in mind. Anyway, okay. So here's the other problem. This to me is equally as bad as the other issue, is that when we have a binary outcome, there's only two cases where it occurs. It's either a 1 or a 0, meaning error itself, right? If we were to predict it not with a logit model, but with a straight linear regression, our error would be one of two values as well, because we would always be subtracting off 0 minus the predicted value or 1 minus predicted value. Right? So the residuals aren't normally distributed. That's one big issue, right? What's left over can only be one of two things. Those two things don't map on a normal distribution, which violates what we said E was in our linear model. But similar to that is that in a Bernoulli variable, in a binary variable, using a Bernoulli distribution, which is, to me, the one distribution we usually use for binary data, the variance of the variable is its mean times 1 minus its mean. If the mean of okay, so we already established the mean of a binary variable is a probability, right? Between 0 and 1, proportion, call that, right? The variance is that probability times 1 minus that probability. So if you know the mean, you know the variance, right? That is a huge difference between linear regression and logistic regression, that dependency. It's so big that if you take some psychometric classes like IRT, it's the reason IRT has information functions that we talk about being a good thing. Whereas the information functions in factor analysis, we never ever talk about because they're actually flat, but they exist. So anyway, if you're getting into, maybe you want to do IRT, this is why IRT actually has non-constant information functions. One of the reasons. But I digress. What do I mean by that? Think of it this way. When you have a coin flip, right? The coin flip. When you have a binary variable, the highest amount of variance in observation has to be when it's a 50-50 chance, right? Think about what happens. I flip a coin, right? 50% chance. There may be runs of ones and zeros, but on the long run, it's 50-50. So there's going to be a mix of zeros and ones, equal numbers of zeros and ones. If that coin had a 0.9 probability, if it was loaded, it would land on heads 0.9. That means 90% of those zeros are ones. And we think of the concept of variance. Variance means how often are the numbers different in a very basic sense. So in a binary variable, because there's only two values, when one value happens to have a high probability, the other value has a low probability, and your variance is decreased significantly. and it's all related to that probability itself, the mean. So big problems with mean and variance. What am I missing? How am I doing? Okay. Okay. So what do we do? What's the core? There was a normal distribution right up here. Y minus a predicted value of y over a residual variance or variance. That's a standard univariate normal. Sometimes we call this a density function, and this stands for probability density function. It's sort of where the mass of the distribution shows up. You'll note for the normal distribution, this y hat, whenever I describe this here, I just usually put a mean in there, mainly because there's two parameters. There's a mean and a variance. Y hat would be where the mean goes. And in a linear regression, the predicted value that comes from y hat is its conditional mean. That's where that shows up, okay? But the key in the normal distribution, 2 points. Number one, two parameters, a mean and the variance. And number two, this Wikipedia plot here, the range of x goes across the real number line. Those are the two problems with using a normal distribution for the binary data. So the alternative is this thing called Bernoulli. Bernoulli, I don't know much about. I believe was implicated in gambling way back in the day. Listen, all of statistics comes from things you shouldn't do. Right? Remember the t-test? Do you remember where it was created? Where? Guinness. For quality control about beer. Well, Bernoulli, roulette. Gambling with outcomes. Gambling. So statistics is booze and gambling. All right? Just put it that way. And if anybody says, why are you studying statistics? Because I know how to have a good time. Is what you need to tell them. All right? Let's talk about gambling, though. For Bernoulli, this probability looks very different. Sometimes this is the difference in the normal with the this parameter ranging between, or sorry, the outcome itself ranging between negative infinity and positive infinity. Those that value is called continuous. It's a continuous outcome, continuous distribution. Bernoulli is discrete or categorical, right? It has very separate places. So here on the left, you have a 0, and here on the right, you have a 1, right? It's not the number line. It's a bar graph, not a line graph, but a bar graph, right? It's a very big difference. In a discrete distribution, sometimes the PDF is called a probability mass function. It functions the same. There's a little bit more interpretation you can give it, meaning that the outcome of this is the probability of an event occurring, whereas the outcome of a normal distribution is the relative likelihood. It's not a probability. I'm getting into a little bit of the weeds, but I want you to think about that. But here, the probability is P. So what happens in the Bernoulli, so if you say, what's the probability of hitting a heads, that's 0.5 raised to whether or not 0.5 occurred. The probability of tails is 1 minus 0.5 raised to whether or not you didn't observe tails, right? So this function right here is the core of what we use to estimate our model. Right? It is a distribution function. It serves it. We will flip this in just a bit and want to estimate P. Right now, what you see is Y can be 0 or 1, and there's different values of P for each Y, right? Complementary probabilities. Later on, what we're going to understand is, wait a minute, we can use this function. I observed my Y. I don't know what P is. So I can use this function to try to guess what the probability should be. And that's where our logit ends up going. This probability right there gets replaced by the inverse link function and our linear predictor. And so when it goes in there, now this is how we're not actually transforming our data. We're making a little bit of a catch in the likelihood function to allow for continuous terms to be in it. So here, we look at logit. Remember, logit is the log of the odds of a probability of a 1, right? We can model the outcome with that. If you like odds, the odds of this is actually taking the right-hand side of the logit model and exponentiating it. right? That's the odds that occurs. I hate that line. I rarely ever talk about odds in the whole thing. I may talk about odds of various parameters or not. But here's the catch. This last term is the key thing, is the inverse link function. This term right here takes our parameters and our predictors, right? The term in the exponent, both in the numerator and the denominator, that's the ranges between negative infinity and positive infinity. That's the real number line there. So this is what's happening when we go and do a link function, right? We plug in predictors. We put them into this function right here to get them into a probability, right? We don't know what the betas are, but we're going to try some values and guess them. And we need to use a Bernoulli distribution. So we make some guesses as to the betas. We put them in this function. We go back over here, and now we have a probability for each person because we've transformed their predictors and our betas into an expected value or a probability. And now we can see how likely it is that occurred. That's the tie, right? So it's not about the data at all. And we're not transforming the data. The link function does not apply to the data. It only applies to this p parameter, which is the mean of the Bernoulli distribution. How are we doing with that? I wish I would have learned that earlier. When I first learned logistic regression, I didn't get it. I didn't see how it connected. And then in grad school, someone made me do it in Excel. Like literally like plug in your linear predictor, right? I had a column that had just beta 0 plus beta 1 times x. I had some random x's. And then I converted that into a probability using this inverse link function. And then I, for each person, figured out how likely it was, their data, their observation was based on that as well, right? So it's sort of a daisy chain of steps, if you will. I don't know if that's the right term, but sort of linking things together. But that's how it all works together to build what we would call a logistic regression, right? This is a very specific term. How are we doing? Is this helping? This, I understand where you're at. If you didn't get it the first time, believe me, you're not alone. And if you're like me, it would have taken years to figure this out. But you're probably better than me, so I'm good with that. All right. Now, you can, when you do a logistic regression, we still get our betas, and that's where our story, our hypotheses are tested in our model, or combinations of the betas, just like in linear regression, right? What we can get out of this is we can convert between the three, though, right? So if we look at, if we wanted the predicted logit outcome, we could just sum this together and get a y hat, just like in linear regression. But y hat doesn't do us any good. Like, oh, you're like, go ahead and tell someone their predicted logit's 4.2. They're going to look at you like, I don't even know what that means, right? Honestly, I don't know what that means. 4.2, I think, is like 0.9, though, right? So we can flip that logit. Let's go to probability first. Take e to the logit over 1 plus e to the logit, and you get it in probability. Oh, the predicted probability this event happens is 0.9. That sounds so much nicer than a logit. And then if you're super brave, you could go odds. The odds of this happening is, but all to get to odds, all you have to do is take e to the logit, right? So e to the logit is odds. And if you divide that by 1 plus e to the logit, you get probability. How are we doing? So that's the whole thing. That's the whole thing right here. She calls it unlogit. If you want to take the slope, if you want to take one of the parameters and interpret that, you can do that too. And do you have a question? You can answer. Are you okay? EXP is, pardon me, it's Euler's constant. It's a number 2.71, but we raise that to the power of the value. So it's EXP, it's E or 2.71 raised to whatever's in the parentheses. Does that help? It's 2.71, yeah. And the way, this is the name of the person. It looks like Euler in English, but it's a German name, and I'm trying to learn German, and I'm really bad at it, but I believe that's Euler in German. Like Euros, whatever. Anyway, But that's whenever you see EXP, it's basically that's the base, and then whatever's in the parentheses is being raised. It's 2.7 raised to that power. Exponentiate. Euler's constant sometimes just goes by the letter E. It's that like mathematically significant. It's a big deal for a lot of people. So I don't understand that. Why it's that big of a deal? And all of the people in math are gonna send me hate mail. Good news is that, well, I guess I'm not. This is on Lisa's channel. She gets lots of traffic. I can be on my channel and no one pays attention, right? Like Lisa is the Mr. Beast of generalized. That's what I want to say. Write that down too. The Mr. Beast of generalized. She's the Mr. Beast of generalized. Yes. I'm the Chandler in this equation. I'm just here running the channel while Mr. Beast is off doing whatever. Anyway, never mind. Don't come at me, math people. Let's just do that. All right, got a few minutes left. Okay. Here, there is a catch. Sometimes you see intercepts in the model. Sometimes you see thresholds. Turns out an intercept is -1 times the threshold. Now, why is that the case? It turns out if you choose to model the probability of a 0 rather than the probability of a 1, what's changed about it? Turns out the regression slopes, the beta 1 and beta 2, like if let's do it this way. Vladimir runs this model with the probability of 1, and I'm being difficult, and I run it with the probability of 0. Vladimir's and I's results will be identical for beta 1 and beta 2. But his beta 0 will be -1 times my beta 0. And depending on who coded that program in the computer, sometimes they're modeling by default the probability of 0, and sometimes they're modeling by default the probability of 1. And that's why the language is different. So when you look at the program and it says threshold, you will know it's modeling the lower category, right? The lowest probability of a 0. If you look in the program and it says intercept, that means it's usually modeling the probability of a 1. And you can always convert them by just multiplying whatever that is by -1. That's that. It also maps onto, if you think of what's happening in the logit itself, this crazy logit right here, if we were to add error to this and make this truly like a linear regression, the error term for it would follow what's something called a logistic distribution. I never think that really helps. I never like talking about that. So I just usually minimize it, right? But in some places, we do need to mention one thing. As you go on and on in logit models, the variance will become important on the logit scale. Just like residual variance happened in linear regression, right? You don't see an E here. It's a predicted value. It's part of the reason why. But there actually is one there. It's just we never talk about it because its variance is constant, right? The variance of something on the logit scale, here's another statistics trivia for you, 3.29. Was it the last class I talked about Trivial Pursuit? Like was it this class? Yeah, if you're in that stat Trivial Pursuit game, 3.29 is a good one as well too. What's the variance of a logistic distribution? It's actually pi squared over 3 times some constant, but that constant gets set to 1 because we can't actually estimate it. Pi squared over 3 is approximately 3.29, where pi is the number 3.14. So you will not need this very much in this class. But if you want to do a multi-level model with a binary outcome, that becomes important because you need that level 1 variance is involved in pseudo R squared, describing how much variation is explained at level 1, and other features of the model as well too. I'm blanking on those, but that's important. That's where it comes from. And that's also where the threshold idea comes from as well. All right, 2 more quick slides. Turns out there's more than one way to change a probability into a continuous value that goes across the number line. Logit is probably the most famous because it fits with logistic regression. There is an alternative way called a probit. A probit God, here we go. I don't know what I want to spring this on you with 2 minutes left in class. Tell you what, I'm going to stop here because I'm the sub and I can choose that. And we're going to let Lisa pick up with Probits when she comes back. That sound good? That sounds good. Does anybody have any questions for me before I head out?
How much of this do you need to do by hand?
None of it. In fact, you should never do anything by hand. You know why? Number one, it's not replicable. Number two, the rounding error of a computer is far less than the simple mistakes you'll make with attention. I guess by hand, if you do write down your steps, you can do that. But no, it's all computer package based. Good question. Other questions? All right. I will not see you Thursday. I'm being told that they're in closing arguments now. So, long story short, maybe they can deliberate and get this done today, and she's back, and we're all happy about that. But don't forget, when she says "Happy Garbage Day," ask her, "Is it happy? Are you sure it's happy? Has it been happy for you? Is your garbage happy? What's happy about garbage?" Anyway. I'm ruining her channel's mojo now. Anyway, thanks everybody for paying attention. I hope it was worth your time. Good to see you all. Catch you some other time.